or multiple classes, but you know, in case of multiple classes, the decision rule will be one-to-one always. So you need to decide, I don't know, if there is two classes, or if you are female or male, or if the female are behaving different from male, or you know, these are two classes. But you know, the binary decision for two classes says that, for instance, if we want to estimate what is the dropout probability of a student when enters a polytechnical, okay? And we want to estimate if the student succeed or not. Now this one is a binary variable, because for every student, you know, this involves two variables, which involves two states, which is you pass, you continue the university, or you drop sometime. So now that is a binary variable, okay? So let's discuss about the logistic regression in this way. So let's say that, PU equal 1 means success. PU equal 0 is failure, okay? So the probability that U equal 1, so which is the probability of success, is P. So the probability of failure is 1 over minus P. So we want to predict, okay, which is same before, okay? We want to predict not a continuous variable as we made with the estimation procedure, but we want to predict the failure probability of a student or the success probability of a student. So you know, now in order to say that, we need to use something, okay? Because it does not depend on the phase or whatever, okay? So then, in order to be serious on making this kind of binary variable estimation, the dropout prediction, what we need to describe the success probability in terms of a function of another set of variables. So these other variables are called features. Okay? And features are, I don't know, for instance, might be obedience, because it's a research we did. Okay, it's a research activity that we did in the past 2 years. And so you know, you can decide the success probability depending on the sex. Male or female are more successful or less successful. So we put these as a variable. You can put if it is Italian or foreign. You can put, you know, according to different country. Okay? And so where these features are going. Now, in order to account for these features, these features are taken into account, okay, onto a set of variable A. So you know, I have the variable A that depends on these set of features. So I have the probability, success probability, P. That is a function, okay, on the person, but you know, essentially it depends on the set of parameters. And these are the features. Okay, so you know, these features can be organized into a set of features. And now this one can be, you know, sex. This can be, you know, the country, and blah blah blah. But then, you know, it might depend on the grade of passing exam 1. Okay, grade of passing exam 2. Okay, and I don't know. How many attempt of exam 1, and so forth. Okay, so these are variables. Now, for instance, if I need to indicate the sex, since we manipulate numbers, so I take the sex and then I associate the sex to binary variable. And so I don't know, I mean, the 0 can be a male and 1 can be a female. Okay, about the sex. Then the country. The country means that, you know, I indicate by label every country. You know, Italy is 1, blah, 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 and so on, okay? And then, that's another indicator. So the grade is already numbered, okay? And the number of attempts, okay, is still a number. So what we can do is that we can combine linearly these variables. And so we can put all these variables and combine linearly. And then my probability is depending linearly on these variables. This is exactly what is indicated here. So, you know, these features. Okay. This is age is the feature, so age is the feature for one student, for a second, for a third, and so on. So I can make, you know, the dependency on probability from the features, but according to this function, and this function is called the logistic model. So now, looking at that, you know, first of all, we notice that this function is normalized to 1. So the maximum value can be 1. And can be 0 in case of some combination of the parameters. Okay, so in case this one is very big. So now, it is more convenient rather than, you know, treating the probability, it is more convenient to calculate the logarithmic of probability. And if we calculate the logarithm of probability, that we start Friday, okay. This is called the log likelihood ratio, okay. And so according to that, you know, is the log likelihood ratio of the probability. This rewriting all that is linear. So we have a linear model in logarithmic, okay, once again, is in logarithmic. And so we can calculate the parameter according to the set of experiments. So these experiments are, you know, all the outcome of our data set. So in order to make this kind of analysis, you need to have a big, very big data set. And from the big data set, you can estimate the features. So for the student, we use the the data set that was 300 or 400,000 record, okay, which was all the students polytechnical of the last 10 years, I guess, or something like that, okay? So, you know, using that, you can get this success probability, and you can get the dependency. So the dependency is according to this coefficient there. So my unknown is that, you know, we need to get this coefficient A. Okay, so this one here. And so there is an additional term, which is B, is a constant term. Okay? So my unknown is to find the coefficient A and the coefficient B that are able to describe the success probability for every student according to the set of parameters. Now, how big is the set of variables? Now, you know, I can use many features, or I can use the minimum number of features. So we know that if we use a less parameter, and we estimate less parameter, it's beneficial for the accuracy of an estimator. This is something that we know. Now it's similarly here. If we use a less number of features, it is more reliable, more robust in terms of binary prediction. So rather than using the attempted exam 1, 2, 3, blah, blah, we use the mean. Use the mean of the exam and the mean of the attempted. And this way you really compacted the number of variables that we use. Which means the vector, the number of unknown, remember this is a vector of, the linear, the set of coefficient which is taking all the features, okay, these are the features, this is the age. Okay. So, and these are the features for the student I, for instance, okay? So, then we know, that means that there is a multiplier, which is this vector here, which is multiplying all the features. Remember, I mean, I'm mixing up variables that are not homogeneous. For instance, I have a sex, a country, blah, blah, blah. But you know, what I did is, and what we did, and what you can do, is that you can linearly combine and put into the logistic regression function and estimate the coefficient A and the coefficient B. Once you get that, you know the prediction of the binary probability P. So this means in our case is that you can predict, for instance, according to the parameter of each individual student, if the student is succeeding or not, with a certain accuracy, okay? So, you will discuss about this tomorrow, okay? This is one aspect that you will discuss. We will discuss, I will be in the room, but you know, I mean, you start with Matera tomorrow. The first hour will be to prepare you to the to work together, to the kind of exercise. And then probably this afternoon I put on Dropbox the data, which is quite huge because you know you will work on a huge amount of data, big data if you like. And then Matera is cutting the data to reduce the size so that you treat as a limited amount of data. So this is one aspect. The other aspect that you will see tomorrow, is that assume that you have a very big data set. This is your data set, okay? Very, very big. And you have a set of records in the data set. I don't know, you have a student, okay, you have a sex, you have a country, you have a grade, blah, 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 okay? So I have a different color. Every line is a student, okay? Every line is a record. Huh? And now, according to that, you have the column, okay, which is describing the success probability, which is P. So this could be 1, 0, this is not passed, not passed, 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 non-passed, and so on. Okay? So this is what you have. Now, how can we check if our predictor or if our logistic regression is correct or not? Remember, we have a binary. Now, what we did with Monte Carlo. In Monte Carlo, you generate your system and you check your system according to the primary bound, for instance, or similar. Okay? Now, these are real data, so you know we need to infer the property of the data. We need to understand what the data is telling us. So, you know, one very common way to understand and to train the system is that you take the big data set and you cut in 2 pieces. In the first part, you use the data set for training. Now, training is nothing else than estimate A and you know the scalar B. Okay. Then according to this estimated value A and B, remember A and B is according to that. Okay. Now, I mean depending on that one, then what I do is I test on the second part of the data set how is accurate my method. So I'm mimicking such as using the training, I'm trying to learn, I'm trying to find the structure in the data such that is condensed into these set of parameters. These are the linear combination of A, vector A and the constant term B. Now, what is the major drawback about that? The drawback is the following. If you take the entire data set and you cut, and imagine you have a, 10 to the power 6 lines, okay? So 10 to the power 6 people, students, I don't know, whatever case. So you randomly choose to select a subset, 10 to the power 4. Okay. So that means that the remaining part is 10 to the minus 6, 10 to the power 6 minus this one that they're used by training. Now, since we choose this training, the reason to choose the training set in a random way is the following. If I don't choose in a random way, it might happen that my logistic parameters A and B perfectly adapt to the data set. Okay? So I find a way to perfectly justify the training set, but not in general. So my parameters are not justifying the entire data set because they are shaped to the subset. They are shaped to the training. So imagine like a person that has to estimate, is a UFO, okay, which comes here from coming from whatever planet, and drops here, and then now the first 3 people meets that this hypothetical person, this hypothetical extraterrestrial, okay, meet is 3 men, then flies away. So what is the opinion of this guy? Is that all the population of the planet is composed by males. So this is the extreme case. So if I take a training set, these training sets are very special. Now this training set might bias the set of the value of the linear the logistic function, which are suboptimal for the others because it's not able to perfectly predict. So if I set my accuracy, that means that my set of parameters I estimate on the training set can be perfectly estimated training set, but badly estimating all the others. So you also will see an example of that, and this is a counterpart of finding the right model, which means finding the correct size of the model. Don't use too many parameters, don't use too few. And be careful on choosing the training set. And the reason for choosing randomly is that if I choose randomly, I don't choose a specific pattern. Okay? Because if I don't choose randomly, imagine that the first enrolled students that we did using, for instance, the data coming from 10 years of data set of students of Polytechnical. And in the early age, the students of Polytechnical were mostly male. Okay? So if I keep the ordering, the chronological ordering there, and then I make my statistics, probably my statistics will be biased by the presence of many males. If I randomly choose the training set, then that means that this is more likely to be trained on the correct size or the correct the population of the students that are currently at Polytechnic. So this is just another example. So you will discuss on that on a specific example. The beginning will be a very simple example of making polynomial regression, then being more complex until the last exercise, the last data set to manipulate is, I think it is 3 to the power 300,000 lines. Okay, so this is the population, the last population for tomorrow.
So this means that we have to choose, for example, every time a different data set as a training, and then try to estimate the probability of success or failure. For example, every time for the other
Yes.
data.
Yes.
Every time we have to change, so randomly choose.
No, you make, you have your own data set, okay? So you can randomly choose the beginning, and then you apply to the second. Otherwise, you can iterate, so you can make several choice in such a way that you refine your let me say, strategy and you on the average, it works fine. But this is similar to the Monte Carlo test that you do. Yeah, there is no difference from my point of view. Okay. So this was, just, I took the commitment with Matera to just trigger you on these two aspects about, the logistic regression and on the choice of the trainings, how is done, how is not done. Okay. So let's do the mandatory exercises for today. Now, as I said, I randomly choose this. So let's go to our mandatory part. So I randomly, pseudo-randomly, let me say, I pseudo-randomly choose some exercise. So 1, 2, I put some results on some preliminary results, and then in case we are over earlier, I go into the exercise on the break, and then I choose others. Now let's start with this exercise. Close the window. Now this exercise is on the autoregressive moving average spectral analysis. So let's read it together. Now consider y is equal to x plus w. So what I do is I immediately represent. So I have x n, and then we superimpose on w n. And this is yn, where w is a white, this thing is a stationary white process such that its power is 1/10. So I indicate somewhere that the power is 1/10. And xn is, xn is alpha minus 1/2 x n minus 2. So is a recursive model. So this one is autoregressive process. And so xn is obtained by alpha n and by a filter that is 1 minus 1/2 z to the minus 2. And it's xn. And alpha n has a power equal 1. Okay? So characterize xn if autoregressive moving angle, blah blah blah. So it's autoregressive order 2. Okay, we see it. No? Now, second, compute the autocorrelation sequence R, Y, Y. On the samples, okay, and the samples are 0, 1, 2, and sketch with due care for some specific values the power spectral density of Y. So, to solve this B, let me solve here. To solve B, we need to use a Euler-Walker. Okay? So now let's write a Euler-Walker. So the Euler-Walker R, so it is R x k plus minus 1 now, right? Plus 1/2 r x k minus 2 is equal to the input power, which is 1, so it is delta k. Okay, so this is the set of equation for the Euler-Walker. So my unknown, remember, the unknown is Rx k for some k. Now, the problem is asking and is helping me that we need to calculate the autocorrelation of y in 0, 1, and 2. So you know my goal is to calculate the Rx in 0, 1, and 2. So let's start. So I mean I start with Rx 0 plus 1 of Rx. It's a 0 minus 2, so it is minus 2, which is 2, is equal to 1. And then this is for k equals 0, so I make a k equal 1. So I make Rx 1 plus 1 of Rx 1, which is 0. 1 minus 2 is minus 1, yes. And then I make a k equal 2, which is Rx 2 plus 1 of Rx 2 minus 2 equals 0 is equal to 0. Now, so from this equation it comes out that Rx1 is equal to 0. Okay. So I have two others. So I combine the other two, and then let me see if I can see something easy. I cannot do by without writing. So I have Rx 0 plus 1 half Rx2 equal 1. And then I have Rx2 plus 1 half Rx0 equals 0. Now if I multiply here by minus 1 half, okay, I mean, just a method, I don't know, the first that comes to my mind. And then the second line is minus 1 of Rx2 minus 1/4 Rx0 equals 0. So I sum now, and summing, and that one is the same, so I have Rx0 plus 1 half Rx2 equal 1. So summing, it is 1 minus 1/4, which is 3/4 Rx0 equal 1. Okay. So I found Rx0. So Rx0 is equal to 1. Rx1 is equal to 0. And then Rx2 is equal to minus, there's no 1. You need to have it. So it's a 4/3. And Rx2 is equal to minus 1/2 times 4/3. Okay, so these are the 3 samples of the autocorrelation. I mean, it's nothing new so far. It's only to prepare the exercise, okay? And so Ry0, Ry1, R1, 2, R. Now Ry0 is Rx0 plus the power of the noise. So that is 4/3 plus 1/10. Ry1 is Rx1 plus 0, 0. Ry2 is Rx2 plus the noise, which is y, it is minus 2/3. So these are the results we were looking for. Now, The exercise in B, still in B, is asking us sketch with due care some specific value of the power spectral density of Yn. Okay. So what is Yn? So Yn is this one. So if I need to calculate the power spectral density, I need to find the position of the poles. So that means there are two poles. So I have 1 plus 1 half z to the minus 2, okay, and then I need to find the position of the poles, which is equal to 0. Okay. So it is equal to z squared equal to minus 1 half. Then that means that it's negative, so you have two poles. Okay. So it's z12 is in 1/4, and then it is in plus minus j. So the way to make it is this way. This one is a j pi. So z12 is equal to 1/2, and then aj pi half, and then it is plus 2 pi divided by 2. So it is. Okay. So I have two poles. One pole is in 1 over square root of 2, which is 0.7. And then I have another pole there. So this is Z1 versus Z2. Now, if I need to sketch the power spectral density, so let's say sketch with care. What does it mean with care? It means that in some points I need to calculate the value of the power spectral density. Okay. So now that means that for this case, is minus pi, 0, pi. So I have two, let me say, peaks in pi divided by 2, minus pi divided by 2. So I have two peaks that should be, what I expect is a behavior approximately like this. Okay? Now, let's see what is the value here. Now the value here, if from here to there, is 1 over square root of 2. This interval is 1 minus 1 over square root of 2. Okay? So how much is the amplitude there? It is, this that goes to the denominator, and then the other distance. The other distance is 1 over square root of 2 plus 1. Okay? So the value here is, let me call the value we indicate some specific point. So it's h pi divided by 2. So in h pi divided by 2, it is 1 divided by, so this distance, which is 1 minus 1 over square root of 2. And then it is the other one, which is 1 plus 1 over square root of 2. Okay. 1 minus 1 half, which is equal to 1 half. Okay.
And there with power of 2?
Yeah, okay. So it is 1 minus 1 half, which is 1 half. So this one makes 2. Now, so since the value is in the square, so it's 4. Okay. Now I compute, this point, which is there. But the value here is the same as there. So because it's perfectly symmetrical. The value in 0, the values in pi is the same. So then you know I need to calculate this distance, which is 1, and here is 1 over square root of 2. So that one is 1 to the square plus 1 half everything to the square root. So it is this value here is 1 to the square plus 1 half square root, okay, and then square, okay, so that's enough. So that is the behavior of power spectral density, which is 1 plus 1 half, which is 3 half. And similarly here, and similarly here. So this is the behavior of the power spectral density over x. Okay. Then the power spectral density of y is the same, shifted up by 1/10. So the power spectral density it is, let me sketch it better. Is shifted up by 1/10. And the reason is because there is a noise superimposed. And the power is 1/10. Okay? So it's shifting up. 1/10. So the value, this is the true power spectral density. This value is 3 half plus 1/10. This peak, which is the same there, is 4 plus 1/10. Okay. So when I ask you to sketch the power spectral density with care, that means that you need to calculate a few points to establish where it is. You can copy it from MATLAB, but then you need to prove me that you make some reasoning to sketch the power spectral density. Okay? I do not accept calculate by MATLAB. This is not the goal of the exercise. Now, so I mean, this is so far everything was just a re-exercise of whole exercise that we did. Now let's start with the new exercise. Derive the moving average spectral analysis for Yn from Rxxk. Okay. Calculated in V. So what does it mean? It means that I have this power spectral density, and you know, I don't know the mechanism of how it is generated, so I don't know that it's white noise superimposed to the autoregressive 2 process. You know, and then I assume that this process is generated as a moving average. So how to compute that? Now, let's take the results. It is quarter. So compute moving average order 2 spectral analysis from RYK. Now, I remember that RYK, let me copy from here. Okay, these are the results that I made previously. Now, if I want to compute the moving average order 1, that means that I am assuming that I generate with the beta and random process with the power sigma square beta. Okay. I am filtering these beta process by a filter that is 1 minus b or plus bz to the minus 1. b1 because it's the order 1. And out of that, it comes an xn. I'm assuming that the process is generated this way. Now, since the process is generated this way, then what I do is I calculate the autocorrelation that I expect here. And now I'm call this x prime. Let's see. So now, how is the autocorrelation there? The autocorrelation here, there is so r x prime z is equal to sigma squared beta, and then it is 1 plus b1z minus 1 plus b1z. So computing, it is sigma squared beta. Now you see sigma squared beta is acting as a scaling factor, okay? It is sigma squared beta multiplied by 1 plus b1 squared plus it is sigma squared beta multiplied by b1 and then z plus z to the minus 1. So what I notice that the autocorrelation, okay, is it contains just one sample different from 0. Now, I know that my autocorrelation is 4 third plus 1/10. Then it is 0 and 1. Then it is minus minus 2/3. And then this is different, okay? So, you know, what I have to do is this. I know that when I need to estimate the moving average spectral analysis, I cannot take the samples as it is, but I better to window. Otherwise, my power spectral density is not a positive density. So, windowing means that I need to apply a window that should be 0 in 2. So this is the kind of window that should apply. Now, this is the window. Okay? Because for the sample 2, it should be 0. But you know, it is 0 already for a sample 1. Okay? So I mean, in principle, let me say, in principle, what I should do is this. I should write a set of equation, which is the following: sigma squared beta, 1 plus b1 squared. Okay, the value in 0 is equal to 4 third plus 1/10. And then I need to write sigma squared beta times b1 equal to 0. So I have a system of equation in 2 equations into a known. Now, you know what I noticed that since sigma squared cannot be equal to 0, then from the second equation, b1 is equal to 0. So, pushing inside in the previous equation, I get that sigma squared beta is equal to 4 third plus 1/10. So to conclude, I conclude that the moving average spectral analysis of order 1 does not exist. So and the filter is a filter that it's not filtering, okay? So B1 is equal to 0. So for this special case, you know, the moving average order 1 is not existing because it's not filtering. There is no filter which is acting as a filter with 1, 0, which is shaping the spectrum in this way. Now, if you think about that, imagine that intuitively you have a 1, 0. You know, if you have 1, 0, you need to put the 1, 0 in such a way that these 1, 0 is representing these well-symmetric power spectral density. That means that you have 1, 0. So you need to take a wide random process and filter to get something that is similar to that. So if you have 1, 0 to put, this 0 goes to the, or to the 0 or to the minimum of these power spectral density. But I mean, according to the shape of this power spectral density, which is perfectly symmetrical between 0 and pi, if I have a 1, 0, I cannot decide if I put here or there. In other words, if I have 1, 0, I cannot decide if I put here or there. So, I mean, if rather than putting a 0 which is favoring one or the other, I decide to give up. And this is why this is the reason why, you know, the power spectral density, the spectral analysis for moving average order 1, I mean, does not exist. Now, let's make the probability is moving average. Okay, let's for 1 second, let's stay on moving average. So let's try with moving average order 2 now. So let's make, you know, since a moving average order 1 does not exist, let's make a moving average order 2. Now, so what I need to do, I need to rewrite my I'm using my autocorrelation that I calculated. So for moving average order 2, what I need to do is have a beta order 2, if you like, but you know, let me write just beta n, which has a power that is sigma squared beta, a new power, which is entering into a moving average filter order 2, which is 1 plus b1z minus 1 plus b2z minus 2. Okay, is a system composed by 2 zeros, and here it is x prime. I want that the power spectral density, so the power spectral density here is coincide with the power spectral density of y. Now to make that, I need to write the autocorrelation. So what is the autocorrelation? Now I start, you know, smoothly. Then I have sigma square b beta 1 plus b1z minus 1 plus b2z minus 2. Now you know, I assume that the coefficients might be complex, for instance. No, it's not possible. So let's avoid too many complications. Now I have 1 plus b1z plus b2z squared. Okay. So I have sigma squared beta time 1 plus b1 squared plus b2 squared plus I have sigma squared beta. Then I have 1 multiplied by b1. So it is b1 is equal to minus 1, and then it is b2 b1. 1 times 1, fine. Then I have a b1 z to the minus 1, which goes here with z minus 1. And then I have a b2 z to the minus 2 multiplied by b1 makes a z to the minus 1. Okay. Z minus 1. I put in column, you will understand in 1 second why. Then I have a sigma squared b multiplied by b2. Okay, so this is the autocorrelation. I computed, one piece after the other. Now, since I want to estimate a moving average spectral analysis, this should be equal. So I should impose the equality. Change the color. This is equal to r y 0. This is equal to r y 1. Okay. So I remove this part and they put equality. I remove this part and they put equality. This is equal to r y 2. And then I need to solve. I have a system with 3 equations and 3 unknowns. Because I have one unknown is sigma beta, the other unknown is b1, the other unknown is b2. The system of equation is not linear. It is not correct doing this way because I need to window. Okay? So I need to apply a window. Now, going back to my set of coefficient, I cannot reuse the same figure. So this is 0, this is 1, this is 2. This one is 4/3 plus 1/10. This is 0. And the other is minus 2/3. Now, if I want to apply, I want to use the autoregressive order 2, what I need to do is I need to apply a window that is going to 0 at the sample 3. So that means that this value, okay, so since it's going to 0 at the sample 3, so this is decreasing by 1/3, 1/3, and 1/3. So it is multiplied by 1/3. So that one is multiplied by 1, which is the window, multiplied by 2/3, that is the window, multiplied by 1/3, that is the window. Okay, it's triangular window. So that is equal to 4/3 plus 1/10. But since ry is ry1 is 0, is 0, right? And then that is 0. And the third equation is ry2, which is minus 2/3 multiplied by 1/3 minus 2/9. So I have to solve this set of equations. So I start with, I don't know, and now it's you can choose whatever your flavor, okay? So you can start with the sigma beta square, okay, and then you have a sigma beta square multiplied by b2, which is minus 2/9. You have a sigma beta square multiplied by b2 here. So you collect b1. I don't know. This is the strategy, okay? So now it's purely computational strategy. Now you need to go back to, use computation. Use non-linear computation. Okay, so I use the sigma beta b2 equal minus 2/9. The last equation. I pull into the second one. The second one is it is b1 multiplied by 1 plus sigma is sigma beta plus sigma square beta v2, and this is equal to 0. Now, since this one is minus 2, 9, and the only possibility for the second equation to be 0 is that sigma beta is equal to this sigma beta, so I have sigma beta minus 2, 9. Okay, so it's a nonlinear equation, so I have many options. Let me write there. So I don't know, for the last one, okay, I have B1 multiplied by sigma square beta minus 2, 9. This is equal to 0. Okay, so it can be either that this guy is equal to 2, 9, or that beta 1 is equal to 0. If this one is true, then beta 2 is equal to 1. Then I go back, okay? Then I start solving with the first. And the first one is sigma beta square 1 plus b1 square plus b2. Okay? And then according to these two hypotheses, I solve it to the first. So if b2 is equal to 1, this is 1 to the square, so it is 1 plus 1 to the square. And then I have an equation where I have sigma beta square, then I have a b1. Okay, so I need to find b1 from here, okay, according to this equation. And then I substitute that. And then I make the second possibility, which is b1 equals 1, equals 0. So I solve this set of equations. Now, my comment is that what I expect intuitively is that the two zeros in moving average order 2, they go here and there. And this is helpful because if I want to model these autoregressive plus noise with a set of zeros, the zeros are pulling to the zero the spectrum. So that means that if I want to model these power spectral density by zeros, the zeros should be put halfway in 0 and in pi. Okay? So what I expect is that I expect that the zeros are here and there. So solving the two equations, usually in moving average, I have a set of equations that gives me two solutions. Gives me one value, one solution, and another solution. Usually I have a two set of solutions or more. And now I ask you, why have more possible solutions? And which one is the best? Now, so then you remember, I'm trying to model my power spectral density by zeros. Okay? But you know, from my equation, beyond the analytical part, from my equation, I mean, how many possible solutions do I have? You know, it's easy to see that the number of solutions are in total 4. Because I might have 2 zeros there, or 2 zeros in a reciprocal position. Or if I consider the possibility that the B1 and B2, so the polynomial is complex, I might have 1 0 here and another 0 here. And then the last one is 1 0 outside and the other 0 inside. Now, where is inside? If This one is Z1, here is Z2. This position is 1 over Z1. Yeah, there it is, 1 over Z2. Or all the combination. That's why I have a multiple solution. Because I'm choosing, according to the polynomial, I'm choosing one possible combination of roots of zeros. Because you know what I'm solving is, I have these autocorrelation, which is the one on the top, and then try to make the power spectral density to be equal to that. So I'm modeling the power spectral density represented by that autocorrelation by a filter that is composed by 2 zeros. Now, where I put the 2 zeros is up to me. And it's up to me because, I mean, might come from the different solutions. So, you know, I mean, when I make the different cases, I should not be surprised that I get a different solution. So if you look at, I don't know, if you talk with you are not supposed to do, but if you talk with your colleague during the exam, it's not surprising that he gets a different results. So which result is correct? They're all 4 correct. They're all 4 correct. Because the power spectral density, since the power spectral density is the combination of the polynomial and the polynomial which is flipped. Okay? So both cases are correct. So summarizing here, since for moving average order 2, 1 has 2 zeros. Okay, so the 2 zeros might be, let me write this way, H moving average over 2, which is 1 plus Z1, Z minus 1 times 1 plus Z2, Z minus 2. Okay. So the power spectral density or the autocorrelation are moving average order 2, Z equal sigma squared beta that I need to find, and then it is 1 plus Z1, Z minus 1, 1 plus Z2, Z minus 1 times 1 plus Z1Z times 1 plus Z2Z. Now, so what I can find as a solution is, I can find as a solution combination of this one and this one. That is a solution number 1. I can find a combination of the Z1 and the Z2 reciprocal. I can find a third combination, which is Z1 reciprocal and Z2, and I can find as a fourth solution the zeros that are reciprocal in the reciprocal position with respect to the solution number 1. So that means that is solution number 1. Possible solution is Z1 and 1 over Z2, which is outside. This is solution number 2. The solution number 3 is a Z1 reciprocal, which is 1 over Z1, and Z2. And the solution number 4 is all outside. 1 over Z1, 1 over Z2. These are all 4 possible solutions. It's not unique. So what we see is that in moving average solution, the arrangement of zeros is not unique. Okay? All these are possible. So if I need to find a minimum phase, then you know number 1 is the minimum phase. And you know, on contrary, number 4 is the maximum phase. So, I mean, if you solve the numerical part, so if you solve the equation, you take answer there. If you solve all the equation, you can find a different solution.
So this because we use the equation, we had 2 possible results, either sigma beta square equal to 12.
Yeah, that's one. Yeah, that's one. And
or b1 equal to 0.
Right, that's one. So you know, I can either choose that one or the other. But if you continue, there is a b1 squared. And so since there is a b1 squared, there is again 2 solutions. And there is b2 squared, and there is again 2 solutions, because my goal is to get b2. So since there is b2 squared, there are other 2 solutions. So another alternative way to find the moving average is that we take this polynomial, so it is this, that one. We find the roots. Okay. And then according to the roots, we selected the minimum phase roots. That was part of the homework 1. In homework 1, the goal is to select the minimum phase roots. Okay? So you know, it's similar here. You need to find the minimum phase roots or maximum phase roots or whatever you decide. It's arbitrary. There is no constraint. If I don't write, for instance, some other condition, like in the homework, I wrote that you need to use a filter that is causal. So if it is causal, then you know you have some constraint. But if I don't give you any constraint, then any combination is possible. Any possible way to pair all the set of, in this case, 2 zeros. So according to the 2 zeros, I have a 2 to the power of 2, which is 4 possible solutions that are all equally valid. So if I need to estimate a moving average order n, arbitrary n, I have in total 2 to the power n possible solutions. There is only one out of the 2 to the power n solution that are minimum phase, and there is only one out of the 2 to the power n solution that is maximum phase. Now for this reason I wanted to solve, the moving average, because I want to discuss about this point. Now, if I need to calculate the autoregressives order 1, which means assume that this is the power spectral density, and you need to place one pole in such a way that it is describing at best this power spectral density. Trouble, because you don't know where to put the pole. Okay? And so since you don't know where to put the pole comes here. Because you don't know where to put the pole. Okay, since you don't know where to put the pole, it's better not placing the pole. So not placing the pole, it comes out that the autoregressive order 1 spectral analysis is 0. Okay, there is no autoregressive 1 spectral analysis. You can find autoregressive 2, but not autoregressive 1. In other words, if you are not happy with this and you want to calculate analytically, then by doing analytically you need to write a Euler Walker. And for autoregressive order 1, you need to put in ratio the autocorrelation in 1 with respect to the autocorrelation in 0. But since the autocorrelation in 1 is 0, so the coefficient is 0. Okay? So you can intuitively solve, you can mathematically solve. And this concludes this exercise. Now, let's see the other. Please try to understand this concept because it's, it's one of those concepts that are binary, which means once you understood, it's really stupid. If you don't understand, it seems magic. Okay? Try to elaborate a little bit. Now I took another one, which is, is from March 2017, 2 years. Okay, so I have alpha and beta. Now I sketch it. But now I have a y1, so y1 is autoregressive. Y1, so half 10, which is going 1 minus 1 half z2 minus 1. I get the y1. Then I get y2 as a moving average, which is z minus 2 plus 1 plus z2, which is y2. And then x is just combining. Now, question is, characterize y1, okay, it's autoregressive. Characterize y2 is a moving average. Sketch with care the power spectral density for y1 and y2. Okay. So this is a pole. And for the other, where is it? And the other, the autocorrelation is, is behaving this way. Now, let's go to our point. So, everything so far up to here is preparatory to the second part, okay? And this one is, everything so far is, should be known to you, so you know how to make it. So what I did, I just copied from the copy that I made, I don't remember. So, the autocorrelation, okay? Now, derive, so let's start the exercise. So the spectral analysis part of the exercise. Derive the moving average spectral analysis for y1 using RY1Y1, which is the autocorrelation here. So this process is autoregressive order 1, which is represented by a pole. So what I'm trying to do is I try to fit a moving average order 1 on the power spectral density calculated for y1, assuming that I know the autocorrelation. Let me open a bracket. In practice, we don't know the autocorrelation. We need to calculate by the sample value. So that means you calculate by the sample value and you do exactly the same steps that we do, okay? By numerical, by math, by whatever. But in the exercise, you use the ensemble autocorrelation in place of the sample autocorrelation because I cannot give you the sample autocorrelation to compute during the result. So since the procedure is the same, then we use this as autocorrelation. Now, derive the moving average spectral analysis from Y1. So in Y1 I have a pole. Let me see, a pole in 1/2, which is giving me a resonance in 0. So let me say the largest amplitude in 0. So what I expect that the moving average is compensating. So what I expect is that the pole goes on the other side, because since the power spectral density is behaving in this way, so since in Y1 I have a pole, and the pole is placed here, and the power spectral density is approximately behaving this way. So the only possibility by using a 0 is that I put the 0 in a position where the power spectral density is as a minimum, and which is in pi. So I expect to have a 0 there, which means approximately it should be here, the 0. This is the 0 for moving average order 1 in this case. Remember, every engineer knows the answer before computing by mathematics. If you don't know the answer before, you're better to change the job. Okay? So you need to know approximately what is the answer before. Now, this comes from practice, but it comes by putting together all the theoretical tools that we discussed. So now, let's move forward. So, how to make the autoregressive spectral analysis, moving average spectral analysis? Now, this autocorrelation, is the autocorrelation for autoregressive one, so it's behaving this way. So this is R, Y1, Y1, okay. So it's decreasing that way. So what I need to do, I need to apply a window. So the window in moving average order 1 should taper to 0 at the sample 2. Okay? So then that means that I should multiply by 1/2 time the autocorrelation R Y1 1. Okay, that's the window. So let's compute it. So the set of equation is now the power in 1, which is 1 minus 1/4 is 4/3. So there's R1 in 0 time the window in 0, which is 4, 3, 4, so 4/3 times 1, and Ry1 times the window in 1, which is this 1/2 divided by 3/4 multiplied by 1 the window. Now, this is equal to what? This is equal to, assuming that I take a white process, and the white process is exciting, so I have a sigma square moving average 1, which is exciting, 1 plus Z1, Z minus 1 over B, we call B, it's easy. BZ minus 1 times 1 plus BZ. So the position 1, so I have a sigma square moving average 1 plus B square plus sigma square moving average 1 which is B1 Z plus Z minus 1. So now, this is the term that goes here, this is the term that goes there. So this one is sigma square moving average order 1 plus B1 square. And the second one is sigma square moving average order 1 times B1. Then I need to solve it. So is it, is it non-linear? It's non-linear because there are the square. Because there is a sigma square and a B1 square. So a system, and I say just, is a system of non-linear equation to solve. By solving, there might be the zero inside or the zero outside of the circle. So I might have two solutions. I might have a solution which is equal to something or something else. So let me solve it tonight. So I got sigma square moving average 1 times B1 equal to, so it is 1/2, 1/2, 3/4, 4, 1/3. Is it 1/3 this one? 1/2, 1/2, 3/4, yes, 1/3. Then I have a sigma square moving average over 1 plus B1. I don't know, I can start solving B1. Okay. So I can say that B1 is equal to 1/3 sigma square A. Then I put B1 inside here. Then I have a sigma square NA1 multiplied by 1 plus B1 square. So it is 1/3 times 1 over sigma square moving average. Everything to the square. This is equal to 4/3. Okay, so sigma square moving average plus 1/9, and then it is 1 over sigma square moving average is equal to 4/3. So I multiply by 9 and I remove this one from the denominator, but this is, so it is sigma square, sigma to the 4th, 9 sigma to the 4th, and then it is minus 12 plus sigma to the square plus 1 equals 0. So it comes a two solution for sigma square. Okay? So you have a two solution for sigma square. Then you take one of the solution for sigma square, then you get B1. You take the other solution for sigma square, you get another value of B1. If you test, you have one position, 1, 0 inside or 1, 0 outside, because you have two solutions for B1, and B1 is setting the position of the 0. beyond the numerical part. Look at it. Try yourself. Please try. Try not to window. Try to apply not the window. Now, what you might expect, if you don't apply the window, is that when you get your system of equation, then you know you ultimately solve it. You get one of the solution, sigma square, which is negative. So you get a power that is negative. So you have one value probably, possibly you have one value that is positive and you have one value that is negative for the power. Negative power is not possible. So why do I have a negative power? I have a negative power because I decided not to window. So if you don't window, let me write so you do it because you see it written. Perhaps you understand 50% what they say, but you know, if you see it written, perhaps you. Okay, so if not window by Wn, the solution is not guaranteed, but you know, most of the case, this is what you get. The solution for sigma square moving average order 1 might be smaller than 0, which means the power is lower than 0. Sigma square is lower than 0. If you like, you know, for those that likes the mathematics of the problem, it comes that sigma is imaginary. Okay? I don't know, then we can questionize on possibility that sigma is imaginary or whatever, okay? Which makes no sense. So physically makes no sense. You can keep on working with the mathematics as long as you like, but you know, physically it makes no sense. Then we stop here, okay? What is the mistake? The mistake is that we are not applying the window. So if not window by Wn, okay, the solution sigma blah blah might be less than 0. Now, I don't remember, there is one exercise that I purposely choose in the past in the moving average order 1 in such a way that the value of sigma square comes to be negative. I did intentionally. I choose purposely the exercise in such a way that if you compute the moving average model, it comes to be less than 0. Okay? And then remember the students, you know, making the moving average spectral analysis, and they come to me and say, it comes smaller than 0, the power, okay? Why is that? You know, so immediately you can see that the reason for that was that they did not apply the triangular window. They did not apply any window that has a Fourier transform that is positive. I could not say that, but you know, so I saw it.
So in this case, if not windowing means that we use a rectangular window.
Yes, that means that my system of equation is copy, just to be more maniacally precise. No. So I take it out of the window, you see? This is the system of equation that I'm writing. Okay? Now I have reviewed. Okay. You see, I'm not applying the window. This is the most intuitive way. You say, okay, why should I apply the window? Then you know, if you solve for this in this setting, I mean, now I don't remember if this was one of the exercises that I purposely choose to be negative in power, to have a negative power. Okay? I don't remember.
And could we have also, I as an example, sigma which is positive with this setting, but for example not reciprocal 0.
No,
No.
impossible. If it is the case, then there is a mistake. So the rule should be, the theory should be fulfilled. So you should have two solutions. One is inside, one is outside. It might come that the power is not consistent, which is, and the reason why it's impossible that the two roots doesn't come inside and outside is because of the way that I formulated the autocorrelation. I force the autocorrelation to have the roots inside and outside. When I write this way, the roots should be inside and outside. So it's not possible. That's the fine. Take a break. Okay.